Our speaker for today is Dr. Fabio Gastaldello, and one moment. Fabio is an observer interested in the physics of clusters and groups of galaxies, as inferred mainly by X-ray observations, but also from observations at other wavelengths like optical and radio. Particularly works on AGN feedback in cool cores, metal abundances in the intercluster medium and intragroup medium, and the characterization of the dynamical state of a system. In addition, galaxy clusters are also important cosmological tools, provided we are able to measure their masses. So this measure can only be done in any different ways, for example, using the X-ray emission, gravitational lensing, or the dynamics of their member galaxies. So without further ado, Fabio from INAF ISF from Milano will talk to us today about the metal content of the hot atmosphere of galaxy groups. And with that, I leave the stage to you. Thank you very much for this first talk of the year, Fabio. We're looking forward to it.
So thanks to Konstantinos and Sam for inviting me to give you this talk about the metal content of the hot atmosphere of galaxy groups. This is basically the results of a series of reviews that were done actually in 2021, I was about to say last year, by a series by a number of people actively working on galaxy groups. So there was one on AGN feedback led by Dominique Eckert, and I was also present in that on that. One on the scaling relation led by Lorenzo Lovisari, and one on fossil growth. So the one that I led in collaboration with Aurora Simeonescu, François Mernier, Kosuke Sato, and Kyoko Matsushita, mainly for the observational part, and Veronica Biffi and Massimo Gaspari for the simulation part. So what I will give you in this talk is basically a summary of this review with a good part of introductory material about the issue of chemical enrichment. I will be back and forth also with the cluster scale, trying to make a comparison, also because, as you will see observationally, there are much more results at the cluster scale with respect to the galaxy groups, simply because the galaxy groups are fainter in X-rays, and we are starting to explore and basically follow the steps of what has been done at the cluster scale. So let's start basically with the general introduction. So where do chemical elements come from? So we know that basically primordial nucleosynthesis only produce hydrogen and helium and traces of the light elements like lithium. All the other elements that we call in astrophysics generally metals are produced ultimately by stars. So basically by supernovae and stellar mass loss and merger of compact stars. So let's introduce the characters. So what are the stars and supernova explosion which are producing the chemical elements? So the first one to consider are core collapse supernovae, more general than the just supernova 2 that were always quoted. So those are massive stars that evolve very quickly, relatively quickly in time scales. So the enrichment caused by supernova core core by supernova core collapse is a very prompt one and closely related in time to the star formation event. They produces mainly the so-called alpha elements, simply because their nucleosynthesis is made by capture of alpha particles. How much of these elements are produced clearly depends on the mass of the star, and this is clearly related to the type of initial mass function related that produces that was produced in that particular star formation event, and from the initial metallicity of the star. Okay, so they exploded and reached quite fast after star formation. So clearly seeing a region of the hot atmosphere, or also the stars in some galaxies which are rich in these alpha elements, point to a further stellar population which were produced, which then form after these initial events, but very closely related in time to that star formation event. The other main character of the supernova enrichment are type 1a supernova. That, as you know, there are still some doubts about the real progenitor. So they are clearly exploding white dwarfs, but it remains to be seen if this is mainly produced by what is called a single degenerate scenario, as you can see in the right-hand side. So a white dwarfs are accreting probably from a low mass donor, which then finally reaches the Chandrasekhar mass and explodes, or if this is more closely related to directly the merger of two white dwarfs, and this is the double degenerate scenario. Okay. So having said this, it was common wisdom that supernova 1a really explode relatively late after the star formation event, up to 10 to the 9 years, so much longer, basically in order of magnitude, longer than the usual 10 to the 7, 10 to the 8, 9 for supernova core collapse. But this is starting to be debate. I would say there is clearly a consensus that probably some supernova 1a explode instead relatively early and much more close in time to the star formation event. And this clearly reflects the great uncertainty in the progenitor scenario, and clearly on the time that the binary needs to evolve. Clearly, if you have to expect the merging of two white dwarfs, clearly you will have a longer time scale with respect to the single degenerate scenario. So those type of supernova clearly produce heavier elements. In particular, all the elements heavier than silicon. Silicon is basically shared half and half with respect to supernova core collapse and supernova 1a. How much of these elements are produced? So clearly depends on the nature of the progenitor, but also on the physics of the explosion. It's very difficult to reproduce the supernova explosion, as it is the case also for core collapse, but even more so for supernova 1a. And much of this also depends basically on the speed of which the flame of disruption propagates through the stellar interior. So if it is below the sound speed in the medium or above that. So if we are in the deflagration or delayed detonation scenario. And this clearly produces a different amount of these elements. Other characters of the chemical elements that we see in stars and in the hot atmosphere of our clusters and groups are then asymptotic giant branch stars. So basically red giants in the latest phases of their evolution, which through stellar winds mainly enrich carbon and nitrogen. So those elements cannot be entirely attributed to supernova explosion, because there is clearly a great production by the stellar wind of the stars. And as we learned, in particular, given also the gravitational wave events, the recent one seen by LIGO, in the merging of neutron stars, then also heavier elements, the one, the precious one, like silver, platinum, and gold are produced. Okay. So this is a nice summary actually from Wikipedia, where you can see the periodic table and what is the ultimate origin of the elements we see. And clearly those are a little bit out of reach from us, but the X-ray band is wonderful because basically we can trace elements basically from carbon up to nickel and probably also copper. So here just a quick summary because the material to work is really big. So what are we talking about when we talk about the hot atmospheres? Those are clearly what we will call ICM, the intercluster medium, or the intragroup medium. Okay, so this is the main baryonic component, the one that clearly makes more for the total baryonic matter, at least at the cluster scale, initially traced in the optical by overdensity of galaxies, also the group scale. Clearly, this is the more important material in terms of mass, and it is generally hot, so from 10 to 100 millions of Kelvin, or as we are more keen in the X-ray band, we usually term that by keV. So let's say the total energy of the gas. So basically clusters are on average temperature between 2 and 10 keV. Groups are less than, let's say, 2 keV. They're tenuous because they are basically from 10 to the minus 4 free particle per centimeter cube, or 1 particle per decimeter cube in the basically for most of the volume. They emit by Bremsstrahlung because clearly at those temperatures the material, the gases in terms of plasma, hydrogen and helium, are completely ionized. And as you will see, we will see the signature of heavier elements simply because they are able to retain 1, 2, or in the case of the heavier elements like iron, for low temperature of groups, 5, 6 electrons, and we see the bound transition of these, let's say, helium-like or hydrogen-like ions. It is in collisional ionization equilibrium, basically in the form as was put forward, and we started to study as for the corona of our sun. And as you will see, because there is a direct implication on how we measure the abundances given an emission line, it is optically thin, meaning that basically a photon produced by a Bremsstrahlung event can basically reach the observer basically untouched by scattering or absorption. So why are we talking about elements in those atmosphere? In principle, this could have been just pristine plasma, just composed of hydrogen and helium. It was one of the key measurements at the cluster scale made relatively early in the X-ray history by Ariel 5, that by looking at the Perseus cluster, it found evidence. Here you can see the prominent at the cluster scale 6.7 keV iron line, which comes from a helium-like transition, so the iron able to retain 2 electrons. And this measurement was really key because he proved the interplay between galaxies and hot atmosphere. So the ICM is enriched, and given the fact that only stars in galaxies can produce those elements, as you will see, there are all the other elements that we can see in the line-rich X-ray spectra of clusters and group. And this proves really that there was this interplay, and that chemical elements are tracers of structural formation out to cosmological scale. So we do see that chemical elements permeates basically the large cosmological volumes that we can see, up to cluster scales and even to filaments in the case of WIM scale. And incidentally, clearly, this was also the key signature that the emission in those early days, that the emission from cluster was really thermal from hot plasma, and not, for example, inverse Compton by the many radio sources that were already known to be present in clusters since basically the 30s. So how can that happen? So how can we transport metal from the, let's say, the interiors of galaxies up to those cosmological scales? And there is really no shortage of processes. We can basically broadly characterize those as, let's say, galactic winds. We do see some analogs, for example, of galactic winds just made from starbus, and this is a particularly local one, the one of M82, where we do see from the disk then relatively hot plasma and very enriched in metals, basically escaping from the disk. If in this picture was plotted, there are a lot of supernova remnants, actually young supernova remnants here caused by the starbus, and this is really a way to transport metals out of the galaxies. Even more importantly, as we basically realized in the last 20 years, also given the observation in the X-ray bands of AGN feedback at the central of clusters and groups, the both radiative, let's say at the quasar phase early on, and mechanical feedback by AGN, this is caused by radio jets, are powerful mechanism to basically bring metals, expel gas, and enrich gas with that in the surrounding of the galaxies. So you can see here basically a collection of the more difficult to obtain signature of the quasar feedback, but it is basically now clear that there are winds moving at relativistic speeds. So basically here you can see for example, in this plot by the review by Andy Fabian of a distribution of local quasars, let's say local quasars, given the velocity of their winds in terms of fraction of the light speed. You can see absorption of the 6.7 K line here, blue shifted by basically 0.2 C at much higher energies, and also from HALMA and other IFU measurements of really high velocity winds. Here, as you can see, a more closer analog in terms of the this is M87 in Virgo, and you can see basically traced by the radio emission the outflow of gas and metals caused by the interaction of the radio jets with the surrounding ICM. Other processes are instead more related to the interaction of galaxies between themselves here, for example, the antennae, this kind of mergers clearly will disperse metals in the surrounding of the galaxies, and also around pressure stripping. Here you can see the beautiful image of M86 in Virgo, where you can see basically the stripping of the enriched hot atmospheres themselves. Clearly, these mechanisms operate at later times, where the most of the mass of the halos of clusters and groups are already formed, and they are mass environment dependent. Okay, so for example, run pressure is more prominent in massive clusters, so I can already anticipate that those are relevant, but they are not producing the bulk of the metal transport, because otherwise you will see observational evidence that we don't have. So for example, if run pressure stripping was the only mechanism to operate, you will see clearly a mass dependence of the enrichment, because run pressure operates more in massive clusters where the velocities are higher. So here, just to show you some beautiful spectra, basically the more rich ones in terms of counts provided by XMM, because it is the higher effective area X-ray telescope now in the market for the last 20 years. You can see here the Xray Spectra of M87, which is really the closest one, and the ones showing basically the most beautiful lines. And you can see here in one of my early papers during my PhD, basically all the elements produced, given the lower temperature of XMM, you can see that iron is mainly shown by this broad feature, which is unresolved CCD spectra, and which is basically arises from hundreds of transition from exactly the so-called L-Shen lines of irons. So from ions of irons, which are able to retain from 4 to 6, 7 electrons. Instead, here from the Perseus clusters, you can see the lines from the helium-like and hydrogen-like iron, and also the elements here. Just you can see, I was modeling that. You can see, if you don't do that, how it arises from nickel. So the X-ray spectra, in particular the one from the modern telescopes, are beautifully rich in lines from the elements, and we can basically trace, exactly as I said, mainly from transition of hydrogen and helium-like ions. Here, just to show you what are we really talking about, basically many years of X-ray astronomy are shown in terms of spectral resolution. And just to show you that, we call it X-ray spectroscopy, but we are far in terms of resolution. Here, by that I mean E over delta E in terms of resolution of our instruments. And you can see basically how the Perseus spectrum changes from gas proportional counters to CCD, the ones that we are used here. And unfortunately, with the only single shot example of a calorimeter of the observation of Itomi of Perseus, but you can see what are the prospects of using calorimeters, even more so for the modern ones, like, for example, Athena, which is planned to have around 2 eV. And you can see basically here in red was the previous CCD spectrum, how by going to high resolution spectra, we can show the fine structure of our lines, which instead are multiplets, and how basically by going with increasing spectral resolution, this pops up over the continuum. So here, with spectra like that, we will really call ourselves X-ray spectroscopy, and we will spectroscopists, and we will start to do really the kind of physics that we are used at other wavelengths once you have a spectra. So here, then I will shift gears. I try to conclude here in introduction. I will give really in a number of bullet points the results at the scale of clusters that have been reached mainly thanks to XMM at the cluster scale, because I will continually make comparison then for the unfortunately sparse results that we have at the group scale, and what we would like, at least to achieve with current and future instrumentation. So clusters have uniform abundances almost over the entire volume. Okay, here you can see a collection of the more recent results from let's say the best measurements that we can have with XMM and Suzaku at the cluster scale, trying to reach as much as the volume. Here it's in units of R500, so the radius at which we reach 500 times the critical density, and which is basically a good measurement of let's say the hydrostatic volume of the clusters, where we really have the entire volume. Above that, we are really talking about then the area which connects to the filaments of the larger scale structure. And you can see that basically, besides an enhancement in the core, more pronounced, let's say, in relaxed clusters where there is only one BCG setting at the center, at the bottom of the potential well, dynamically active merger clusters show still an enhancement in the core, where there is still, the most of the action, but much less pronounced. But with respect of the core, where there is really possibly complicated physics of the AGN feedback going on, or of the merger, for most of the volume, the overall abundance, mainly the iron abundance we are talking about here, is basically uniform and flat up to the larger radii that we can see. Clusters, and unfortunately we can only do this at the cluster scale, not much redshift span that we can do at the group scale. Clusters have uniform abundances over the entire history. Here you can see a couple of results, but basically we can try to trace also spatially resolved with the problems of not being biased by the core. We are starting to do that, and we have done that. For example, in this paper, I was co-author of this one, and basically, besides probably some change in the core regions, again, over most of the volume of the cluster, we don't see any change in the overall level of abundance of clusters, basically up to redshift 1. Finally, clusters have a uniform chemical composition. So for the objects that we can basically trace, mainly the one from the Cheers sample and from Perseus or some other very, very bright clusters, we can basically then measure not only iron, but all the elements, also the alpha ones, and we can see that the chemical enrichment is basically uniform and consistent to the solar composition, here shown in gray. Actually, as you can appreciate, some of the measurement done at the cluster scale are more precise than the uncertainties we have for our solar neighbor. So all these results are basically consistent. What looks like as the only viable solution, given also the trend that we know of star formation and the AGN activity, let's say, the Matau plot, all of this is consistent with the uniform early enrichment happening at the peak of star formation and of the AGN activity. Clearly, many details needs to be filled in particular, the chemical composition. I will introduce that. You will see the plot in the following slides. The big conundrum at the cluster scale is still that the chemical enrichment is hardly explainable with the current stellar population. And as you will see, I will basically show the most recent results from the XCOP sample by Simona Ghizzardi, the very recent one. But this is a long-standing problem, which basically dates back to the very early measurements of elements in the ICM, and now we are even more refining that and making that appear more clearly, given the better measurements that we are producing. So finally, after this introduction, going to metals and groups. Why should we care, given also the results that we have seen at the cluster scale? Well, groups are important because they host the majority of matter and possibly of metals. It is important to investigate the metal budgets in different types of systems, as we can really learn how the chemical enrichment, and also the chemical enrichment, as I told you, it's connected to structure formation. So we can really see that metals link stars and dot plasma. And we have a very different mixing groups with respect to clusters. So here what you can see in this plot, it's the fact that you can see the trend of stellar fraction as a function of the mass of the halo. And as you can see that at the group scale, basically by that I mean the M500 for the purpose of this talk, between 10 to the 13 and 10 to the 14 solar masses with respect to the cluster scale, which is in this decade. Okay, so groups have a higher stellar fraction and a much lower gas in the intergroup medium. Okay, and we all suspect that this is clearly related to the fact that feedback is more effective in this range, simply because the energy input is comparable to the one that to the binding energy of the halo, and this is basically the ultimate cause of the loss of cell similarity that we would expect if only gravity was in action. So technically, I show you the lines. How can we measure abundances in the intergroup medium? Well, the fact that the emission from the intergroup medium and the ICM is optically thin, we do not have to use radiative transfer or other complications which are in other fields of astrophysics. So given the fact that both Bremsstrahlung and line emission are basically two-body processes, okay, so one directed from the hydrogen mainly and helium, and the one from the ion and the electrons. Basically, just a measure of the equivalent width of the lines tells you directly the relative abundance of the ions with respect basically to hydrogen. Okay, so what we really do in the, let's say, in the practicality of our work is to use plasma codes like APEC in XPEC or the SpecSat in SPECS. Those are the two most used and applied plasma codes to our spectra, which have basically incorporated the details of many transition that we do see in our spectra. As you can see from this plot, you can see that with respect to clusters in groups, we do see a more prominent contribution from line cooling. And in particular, as you will see from this prominent iron L shell transition, that it really dominates our X-ray spectrum. So this feature, it has been a gift because it makes the emission much brighter. So if the intragroup medium was not enriched by iron, it would have been really fainter. But it's also a curse because arising from hundreds of lines, it has been historically difficult to model. So, for example, here I just show you again with an historical approach. This is the ASCA spectrum of the Centaurus cluster when you started to have higher resolution between quotation marks, because this is still CCD-like, but already at CCD-like at that time, it was clear that the available spectral code like Mika or Raymond Smith were not able to reproduce the structure. And this was, for example, spurred the work which introduced the L in the Mika code by Lidl. So basically trying to model and to put more lines in the L shell lines. This is still the case even in more recent time. You can see, a very provocative title in this appendix by Michael Lowenstein, that in particular, at the cluster scale, objects of 1 keV, still there was a room of improvement going from one version of the APEC code with respect to the previous one. And clearly this made the difference for some of the inferences we make from this spectra, as I will talk basically within 2 slides. For example, the fact that there can be misestimate of the plasma temperature and metal abundances, or false statistical preferences, let's say, for a multi-phase nature, it's called 2 temperature of the plasma, in particular in the course. So is that hopeless? I would say no. I think, and in particular, this was a nice work that we showed in our review. You can see that basically both the 2 competing codes. So here on the left-hand side, you can see the evolution of AtomDB with respect to the latest version of specs, and basically the symmetric approach on the right-hand side. And basically you can see that as time progresses, as the calculation progress, but also the benchmark with laboratory astrophysics. This is a field where you can do laboratory astrophysics and go, for example, to electron beam ion traps and really try to measure what can be the line emission from a particular transition of iron at this temperature. And as you can see, the differences are starting to be close, and you can see how by introducing much more lines, the feature gets broader and higher. Okay, so the more recent comparison really point to a level of agreement of 5-10% at 1 keV, which is the critical temperature for the group scale. So this is probably not the final goal, but this is to show you that the situation has improved a lot. Thanks also from thanks to the Xray spectra that we have seen, and we can basically hope that with higher resolution spectra provided by the calorimeter of the future generation, already by GRISM, we will even further improve this situation. So why did we talk about preference of multi-temperature? Because the iron L shell emission is, given the fact that it is so broad, it basically happens at the peak of our effective area. So where we are seeing a lot of counts and it basically dominates the spectrum, it can basically, it is difficult then to measure the continuum, and it is sensitive and prone to the presence of multi-temperature spectra. So if we are not aware of that, and you fit this emission with the single spectrum, as it is normally, routinely done, even though now, we are much more aware of the problem, which basically arises already from the ASCA data. This was the seminal paper by David Biot who introduced this problem. If you fit with the single temperature a broader emission from the iron L shell, that basically what the fitting code is trying to do is basically rising the continuum to amend for this broad feature that it cannot reproduce with the single temperature spectrum, and this will basically bias the abundances law. Okay, so this is a feature to be aware of, in particular in the core of groups, or maybe in a similar fashion in the outskirts. So just to give you a very quick historical picture, the early measurements with ROSAT and ASCA, which were the satellites, were really starting to probe, to reveal and to probe that also groups, not only clusters, have X-ray emission, have some early puzzling results. So here you can see from an early compilation by Renzini that already at the cluster scale there was, uniformity in terms of chemical enrichment. That now, we have much better data to show that. And this was already, for example, a results which argued against a key relevance, for example, of run pressure stripping in the metal distribution of clusters. At the group scale, there was a huge scatter. So going from solar abundances to puzzling low abundances. And we can really see that this was the effect, in particular on this region. Here it's simply because there were sampled the highly enriched cores, because this was the only emission that we were able to probe with that low effective area, low sensitivity satellites. This was the effect of the iron bias introduced. Where you were able to do, and this was what mainly caused the realization of the multi-temperature nature, if you were doing just a large aperture, in the general trend of temperature distribution as a function of radius of groups. Because basically groups, in particular the one that are X-ray bright, behaves like relaxed clusters. So they have a cool core with a temperature which is rising at the peak and then declining in the outskirts. And those show the usual profiles of relaxed clusters that I also introduced before. So what is the current status of abundance profiles at the group scale, given the fact, and this is a key difference with respect to clusters, that we have much poorer samples, so we are able to follow the abundances only on relatively sparse sample, as you can see here. So, for example, 21 groups from Cheers, or 13 groups from Lovisari and Raiprick, and those are basically able to follow only to some fractions of R500 of the groups. Only thanks to Suzaku, for example, we have been able to try to push the abundance measurements out to R500, or even in the four brightest groups, which are the ones also on the high flux sample, out to R200. But again, what we can tentatively see, given still this sparse result, but results that basically groups follow the same general trends of clusters, and they are basically reaching the same level of uniform abundance throughout their, at least a fraction of the volume that we are able to see, we are able to probe. So here, in summary, what I said: metallicity increase towards the core and decrease outside the core with similar slope. And again, tentatively, it reaches the same plateau as in clusters. So where we do have most of the emissions, so in the core, so where we can probe in a consistent manner the abundances in groups with respect to clusters, we do see that there is more or less the same level. So we can push down to the scale of groups the invariance of mass of enrichment that we have seen at the cluster scale. Much of the scattering in the core is due to the dynamical state, so if it is a merger or not, and the AGN activity. Unfortunately, and I have really to stress that, sample selection with the relative proportion of the categories of relaxed and disturbed systems is key to interpret the results, and we really have still small numbers at the group scale. So why did I say that it is not only the merger but the AGN activity that is causing some of these trends? Well, here you can see some of the poor results that we see, tentative results, because we don't we have examples of merger groups. We are starting to produce that, but it is clearly not as widespread as the cluster scale. Here from early results from Johnson, you can see basically the differences in terms of the abundance profile as a function of R500 between with open dots, a cool core with radio emission. So you can see how the peak of the abundance profile is broadened. This is the interpretation by the AGN activity, by the AGN checks. You can see with filled dots what is, let's say, a relax. There is only, very regular X-ray emission, but no radioactivity. As you can see, on average, the abundance profile is less broadened. And here you can see what has also been already clear at the cluster scale, that merger groups have still, enhancement, but much less pronounced than the one with of cool cores. Again, I will restate, it is critical to establish what is the overall level of the abundance at the group scale, because clearly here we are not probing yet most of the volume, so most of the metal mass, and this is really key for the models of chemical enrichment. So what about the chemical composition? Again, to compare that with the cluster scale, which again is consistent with to be uniform and to be solar. As I said, measuring abundance ratios can in principle constrain the relative contribution of core collapse supernova and supernova 1A. Early ASCA results were controversial because if you were able to measure the iron and silicon, again, these sparse groups, this was pointing to an increasing silicon over iron ratio, meaning that you were reaching a plateau where you could see only the supernova 2 enrichment. I would say that this is no longer the case, thanks to much improved measurements from Suzaku and XMM. We can really see that also at the group scale, it looks like that there is a uniform chemical composition close to the solar abundance. And this again, given also again connected, we don't have a redshift evolution, unfortunately, but as you can see, we can feel the other two elements that favor an early enrichment scenario, also the group scale, which is uniform spatial abundance, uniform abundance at all the spatial scales that we are able to probe, and uniform chemical composition. Okay. Again, compare that with stars. The pattern that we do see in the hot atmospheres with respect to the ones that we see in stars in the galaxies. So here you can see with different legends, let's say in terms of the dispersion velocity of the galaxy, so a proxy for mass. As you can see, the more massive galaxies have higher alpha over iron ratios, and they are closely, really remarkably different from the solar abundances. And this is basically changes when you're going down in mass at the galaxy scale. So this is really makes a constraints on the timing of the delay time of supernova 1A in clusters and also in groups, where we were able to probe even more the chemical composition of the hot atmosphere of groups, because clearly the delay time of supernova 1A cannot be not too early, because otherwise it will pollute the subsequent star generation of stars that we do see in the galaxies, but not too late, because otherwise we won't see these chemical pattern. Metal mass budget. So these the physically meaningful quantities are really not only, let's say, emission weighted or even mass weighted abundances as a function of radius. We really need to integrate those and to compare that with either the stellar light, which is less model dependent, and we can then start to do iron mass ratios. So produce the fraction of iron mass that we have as a function, for example, of K luminosity. As you can see here, it's basically from Suzaku, from some of the objects, so comparing clusters with group scale objects, here as a function of temperature, meaning mass at some fiducial radii. As you can see, those ratios are lower in the inner region of groups with respect to clusters, but they are closer to each other at large radii. Well, if we can prove that, okay, go at R200. So this is also relates to the trend of the gas fraction. And we can try to interpret that, even though there is still a question mark here, that feedback prevented metals to accumulate in the inner regions of their shallower potential wells. Okay, this makes sense, but really needs to be further constrained by the data. In even more meaningful quantity, really directly related to the model of chemical enrichment, is the iron yield. Okay, so what is the iron yield? As you can see, it's the iron mass locked in stars and the IGN. So here it's measured from Xray Spectra, and we can basically integrate that. Here you have to measure the stellar mass in your system, and what we did, you can safely assume that the iron abundance in star is solar. It doesn't change that much the overall measurement that you can do here. And this needs to be sampled. It's a factor with respect to the mass of gas that went into stars. So you have to consider that before stellar mass loss. Here it's basically more or less half the mass that we actually went into stars with respect to the one that we measured here. And what you can do, you can basically compare that with chemical enrichment models, where the key elements to be produced, the key numbers to be produced, are the ones that I show here for the more relevant supernovae, which are producing the elements. So you need to have an estimate of the iron mass produced by supernova events, and you have to have a knowledge of the number of supernovae per unit gas mass turned into stars. And you can basically then produce, either with these gold or brown bands, the difference is mainly due by the supernova 1A rate. If you assume, for example, an higher supernova 1A rate in the cluster with respect to the field, even by a factor of 3, as it looks like it's the case from actual measurement of the supernova 1A rate, that you will get an higher iron yield. But still, by doing so, this is the plot that I've done in my review, where basically we assembled Simona Guizzardi results, the best abundance measurement of the XCOP sample, which is a local one probed with abundance measurement out to R500 in consistent manner. And if you do this calculation, you can see basically a really constraining fact of what I told before, that clearly it looks like that there is much more iron in clusters that the one that the current population of stars is able to produce, even with the most extreme supernova rates. At the group scale, at least within R500, it looks like we are in good shape for the again sparse number that we have. It looks like that we are consistent with the expectation. Unfortunately, this is not a safe conclusion to make, because you really need a full inventory to do those kind of plots under the assumption of a closed system. So if metals can escape or not collapse, then no strong inference can be made. So for cluster, this is secure because we are able to make a satisfactory inventory of both the ICM and the stars within R500. For groups at R500, we are losing a lot of gas with respect, let's say, to the baryonic closure that we expect, let's say, from Big Bang nucleosynthesis. Okay, So this plot should be populated with many more systems, also the cluster scale, and ideally to see the trends at larger radii. So, for example, this is what we are starting to do. And in a recent paper, again, exploiting the Suzaku results for the 4 groups that we are able to probe, thanks to the lower background of Suzaku, out to R200 this way. So basically, more or less twice R500. You can start to see some evidence of what we are suspecting here. Okay. So here it's basically on the left-hand side, the situation I was showing before within R500. Instead, here it's the situation for the objects for which we are able to reach R200. And basically in a paradoxically reverse, here there is mainly only the Perseus, the Perseus point where we are able to measure then the iron K line out to R200. And you can see that also at the group scale, because we are probing consistently the gas and the star, and it was striking for me to see the numbers. Basically, half of the gas mass at the group scale, at least for these groups, was within R500 and R200. And you can see then, if you are able to probe the abundance, which is also still remarkably flat, also at this radii, you can start to see a tension also at the group scale. So quickly, I hope I didn't give you the impression that only calorimeters can produce high resolution spectra. There are also refraction gratings, which are basically using again grating spectrometry to produce high resolution spectra and producing very nice results, and those are consistently produced. Unfortunately, the fact that in X-ray gratings are basically slitless spectra, so for extended sources you have unfortunately a degradation of the spectral resolution. So they are high resolution, but not as high resolution as you would expect, and you are basically mixing a lot of emission coming from different regions, which makes the interpretation of this spectra much more difficult. Clearly, in these respects, calorimeter, even if technically they have a lower spectral resolution, but will be much more straightforward, because then the spectrum will come from a very precise narrow region, relatively narrow region, spatial region of your group or clusters. Having said that, very nice results with RGS, line-rich resolved spectra, and in particular, we are able to probe with high resolution, something you cannot achieve with the CCD spectra, some key elements, like, for example, nitrogen, which looks like to be supersolar. And this is pointing then to clear enrichment from AGB stars. So you can see how having spectral resolution and trying to probe other elements can untap the real potential of trying to use chemistry to reveal the characters of chemical enrichment. And you can, for example, also detect carbon. And even with RGS, you have another proof of a uniform chemical enrichment, also with the oxygen over iron, which is really the key ratio to try to disentangle different contribution of core collapse and supernova A. 2D maps, abundance maps. So not only radial profiles are key, and I would like to have many more examples of this to show the effects, for example, of AGN feedback. As you can see here on the left-hand side, nice results from Ewan O'Sullivan on AWM4. where you can see again traced by the radio jets here in black. You can see that the metal abundance map. You can see that basically AGN feedback is able to entrain and transport metals from the core out to larger radii. Again, there is also the effect of sloshing. Quickly, what happens in a relaxed system like the NGC 5044 groups, which is I always call it the Perseus groups, because it's basically the brightest group in the X-ray sky. Possibly here you can see. Well, you can see on larger radii, larger than the field here seen by the X-ray image, there is a big infalling spirals that you can see it's really distorted in its spiral arms, but their gravitational interaction. And basically this encounter, this merger, set oscillating the gas of the group at the bottom of this potential well, and this is called sloshing. And basically, if you compare the abundance maps showing some residuals with respect to a two-dimensional beta model, where you can really see the enhancement of emission due to oscillation of the gas in the bottom of the potential well, you can see that this motion is also able to transport metals. Here you can see the abundance maps where you see an elongation of the metals of ions in the direction of sloshing. And you can also trace and beautifully see run pressure stripping not only in the X-ray emission but also in the chemical composition. So here, just I won't make justice to my simulation collaborators, but again, just really two slides of comparison of what the hydro simulation can help us in the interpretation and try to constrain the physics of chemical enrichment. So as I told you, we are starting to make observational abundance maps. We are starting to do that also in simulation, and we can see that those abundance maps and making thorough comparison between observations and simulation can help to discriminate AGN feedback models. So, for example, you can see here different realization of different AGN feedback enrichment. So here you can see the so-called chaotic cold accretion, which means basically the explanation put forward in particular by Max Gaspari and also Brian McNamara of the kind of AGN feedback which really works more like the raining, so both positive and negative feedback. Also, it's not only heating the environment but also producing some precipitation, and this gives a very intermittent duty cycle closely related to the recent cooling rates with bubbles, shocks, and entrainment of metals. Instead, if you just do a bondy hot accretion, this drives a continuous AGN feedback with a monolithic, wide, and uniform cylinder of metals. And again, making thorough comparison also with observation, we can hope to try to constrain these enrichment models. The effect of early AGN feedback now, it's not only favored by observation, but we are starting to see that this is necessary also in simulation to reproduce the uniform enrichment at a large radii. So, for example, in this work by Biffy, you can see that if you didn't include the AGN feedback, so you were just using cooling and star formation, basically you would started to see still a declining radial profile, in particular in clusters, but also in groups. This is the case. Instead, to really reproduce the uniform enrichment that we see at all scales, you really need AGN feedback, because then only the energy provided by the AGN feedback is able to evacuate the early forming halos at high redshift and to make metals escape, then to really uniformly enrich the volume that will then later collapse in clusters and also in groups. What are the open questions that we hope we will be able already, possibly with the current observatories, in particular with XMM, we have programs like XGAP, a large program, XMM large program to observe in a uniform way, let's say XCOP like a sample of 40 nearby systems, and Dominique Eckert, Johan O'Sullivan, and myself are co-PI of this system. So what we hope we will be able to do, what is the metal abundance of groups at large radii? Hopefully we will try to reach R500 with XGAP. What is the chemical pattern of groups at large radii? We have basically measurements of really just 4 systems. And as I said, with the metal budget, we really would like to probe the ion yield and the metal budget at different radii, because clearly we need to make a full inventory of the various components at the group scale. We hope we will make progress in the comparison between observation and simulation. And for example, I would suggest that making routinely both on observation and simulation 2-dimensional maps of the metal distribution can help, can foster further progress. And clearly this is more for the next generation of satellites to really trace the evolution with redshift of metallicity in groups. So what is the future? Well, the future is really GRISM. The launch of the calorimeter on GRISM, for which all of us, we hope a much longer life than the one of Hitomi, will provide a giant leap in our understanding of abundances in the intergroup medium for all the reasons that I just said. We will have higher resolution spectra, and we will really able to pinpoint the fine features of the iron shell, and making detailed progress in the numerous transitions that are dominating the Xray spectra of groups. And hopefully we will have we will still have Athena, or new Athena. We will see how it goes through his configuration, and with that we will able really to probe the chemical enrichment at the group scale as a function of redshift. Okay, I'm done. Thanks for the attention.
Great. Many thanks, Fabio, for this wonderful talk, and very explanatory through all the details of metal abundances in groups and clusters. Thank you so much. So a lot of information. Thank you. Lots of details. So let's start with, we have any questions from the audience. If you want to just raise your hand, just speak up, or just you can write it down and I can say it. In the meantime, let me just ask maybe a simple one, just to kick off maybe. Is there expected to be any difference in the metal abundances between non-cooled cores and cooled core groups. I mean, I know it's starting to be studied, but is there anything to be expected of difference, or is it more difficult to do such studies in non-cooled core systems?
Again, it is exactly as you said. So I was really showing in the beginning of the talk this nice abundance map. So, for example, from let's say a group merger, one of the few group merger that we do know in X-rays at the very least. Okay, simply why is that? It is probably a selection bias from the early Rosat survey that we are still using. We hope that Rosita will make further progress in that, in providing candidates, for example. So even for already from the survey data, I don't think that will be the case, but basically also for follow-ups. So having said that, I think you know, besides the difference in the core, which basically mimics the one that we see in clusters for the few systems that we have seen, the reason is that I don't know. In principle, if we look at clusters and modulo the non-gravitational feedback, but if we think that it operates early on, and basically what it did, it was just the evacuate the halo of the already uniform enriched gas, then we should not expect much more action, much more differences. Okay. I think that clearly pinpointing that with all the problems of making reliable abundance measurements in the presence of multi-temperature plasma for, let's say, 1 kV temperatures, because we know that it is really prone to abundance biases. And once you have mergers, you are clearly mixing plasma at different temperature. Okay. So, for example, in a plot like this one, so U1 did, I think this one is clearly 1 temperature. And so, for example, this kind of abundance drops you see in the region, in the central region, is probably due to this effect. Okay, so clearly all of these should be probably on this red color, and clearly U1 discuss this in the paper. So I don't know if that answers your question. I would say no, from if we really believe in this now becoming more solid uniform enrichment scenario from a variety of observational support. I would say that we don't have the data yet, in particular at the group scale, to really probe that.
Yes, thank you very much. So any other questions? Anything from the audience, please? Yep. Let me check. Paul Fallon, thank you for a very interesting and informative presentation. It has been valuable to improve my understanding on metal abundances. Appreciate your explanation of the background. Thank you for your comment, Paul Fallon. Thank you very much.
Thank you, Paul.
We all thank Fabio for this talk.
Sorry, Constantino. So I don't have a question. Also,
yes.
Just a comment. I also just wanted to say thanks, Fabio, for the good overview. So Renier is also here for his PhD, worked on using new stellar yields to improve the chemical enrichment in the Zimba simulation, so cosmological on a larger scale. And one of his applications that we're just starting to look at is the intragroup medium. So this was extremely useful for us to see what we need to look for at Z0 to see if we get it, if we're in the right direction. But it will be global properties. We can't make the maps that you showed in the hydro. simulations, but it's very useful. Thank you.
Thanks. Yeah, that will be really valuable. I think, you know, clearly, I think on the observational side, calorimeter spectra will really help, at least for, let's say, for the plasma codes. Again, I want to be fully clear on this. GRISM will be key. We are really looking forward, you know, having a consistent, not just the Perseus spectrum. But I can already see the limitation of GRISM, because basically it will be photon starved. It is basically 10 times less than the XMM area, and even, you know, 100 times less than, you know, what is on paper still right now for Athena. And it will have a very broad PSF, like any other, you know, previous Japanese satellite. So this will make you know, the fact that we will basically probe the cores of relatively nearby groups. It will be great, don't get me wrong, but then, you know, to really address most of the topics I expressed here, we will really need, let's say, a large area, large effective area, so sensitivity, and very high spectral resolution satellite. Call it New Athena or whatever, but this is what we really need to do. On the other side, again, simulations of all the relevant physics, as it's starting to be, you know, Eagle, Illustrious Energy, all Simba, all these simulations are really helping us in trying to understand the physics and what are the outcome of the various combination of physics. I would also say that, and people around the world, like for example, the group of Nomoto and others, really pinpointing even more, maybe also with the help of observational inputs, these supernova yields will be really critical for all the type of work that I try to illustrate here.
Many thanks. Thank you, Ilani, also for your kind comments. And once again, let's all thank Fabio. Thank you for this wonderful talk. Very
thank you for hosting me. And you know, I'll be up to date with your all your talks. I have seen the one on the YouTube channel, and I will really follow you.
Thank you very much. Thank you very much, everyone, for attending, and many thanks once again, Fabio. Wonderful. Thank you.
Thanks to all of you. Bye bye. Have a good day.
You too. Bye bye.